All right, stat students. So we are going to have a third lesson over these binomial random variables. We've covered a lot of angles so far on how these are created. Yesterday, or the last lesson that we had, we talked about coin flips and a binomial random variable with 50-50 probability. And today we're going to be looking at a new scenario. So let's go ahead and get into it. All right, so this is where we left off in our notes. We did 10 coin flips and we counted the number of heads, which I realized that I messed that up there. And we said, okay, there's 1,024 combinations of getting heads or tails. That's the pathing. If we extended this chart here to 10 places, that's the number, that's the options that you have, heads or tails, okay? And so we're going to do a different scenario today, okay? We are going to start by, and let me do my other display here, move this over. We're going to start by taking a quiz. Now, here's the thing. You'll see it says, are you a good guesser? How confident are you that you would pass this test? That's what we want to say here. So one of the purposes of this lesson is to not only practice more binomial random variables, but also talk about how unlikely you are to pass if you just guess on an entire test, okay? Very, very unlikely, but we're going to actually see those probabilities today. So what I'm going to do is, in your notes, I want you to label 1 through 10, okay? And you can write down A, B, C, D, E for each one of them, and this can be completely random. You can have a pattern with it. It doesn't really matter, but you're going to, after you write those down, when I pause it, you're going to start entering those into play pause it. You're going to get multiple choice questions, 10 of them, and you're just going to click what you picked. So you're taking a test, but you're not really doing anything. You're just randomly guessing. So we are guessing entirely on these, and then I'll give you the results at the end, okay? I think play pause it actually tells you if you got it right or wrong. You don't get multiple attempts on it. It's just going to be right or wrong, and you'll finish the sequence of the multiple choice. So let's go ahead and do that. Okay, so you have taken tests now, 10 questions, and here are the correct answers for this. Okay, here are the correct answers for this. And you can check your work. I don't know if play pause it gives you the score, but if you want to check your answers, you can do that really quick. I'll pause just so that you can count what percent you got correct. Okay, so now you've checked. I think the highest score I've ever gotten on this, and I've done this is my 4th year doing it, is 70%. Somebody actually was able to pass the test, right? And you'll see these questions on here. It says compute x equals 7. Well, that's probability of passing with a 70. This is passing in general here, and then D is probability of failing. And then is it likely that we're going to answer all of these questions? So I would like you to copy these in your notes, these 3 questions. We're actually going to make another one of those probability distributions, just like we did on the other, on our last notes. Let's go ahead and copy these down. First question, is this a probability distribution? Well, how do we do that? We do bins, right? Okay, bins. Is it binary? Well, what's the goal here? Well, that's you're getting the question correct or you're getting it incorrect, and we're counting the number of correct questions. So it is a success or failure. Remember, that's what binary means, success, failure. And in this case, you either got the question right or you got it wrong. Are these independent? Does what you put, or does the result on the first one affect what happens on the next one? No, it doesn't, right? It doesn't affect that. Okay, even if you got it wrong, you may feel like it influences what you put next, but really it's random every single time. And these problems, the first question, the first answer you put should not affect the second. Next, there's a set number of trials. How many trials do we have? 10 trials, right? So there we go. Next, probability of success is the same the whole time. And we're going to list that as P. What is P? What is the probability that we get a question correct by randomly guessing? Well, it's 1 out of 5, right? So 1/5, or as a decimal, which is actually more useful for us, it's 0.2. So we need to write all that down. And yes, it stays 0.2 consistently all the way down, okay? Now we're going to answer B, C, and D. But I want to go ahead and talk about the probability distribution for this, okay? So let's go back to my main display here. And this is what we did yesterday. We had 10 flips. And remember, it's binary the whole way for both of these settings. So if I go, let me go back over here. You know, you're either going to get it correct or incorrect. All right. And if we were to draw the tree diagram like we had up here, it would be correct or incorrect. I'm going to put check mark. I'm just going to go through here and do the symbol. So you got it correct or you missed it. Then you got the next one correct or you missed it. The next one correct or you missed it. Correct, miss. So this is how it's looking identical, right? It's looking pretty much identical to the coin flip. But here's the problem. Are these 50-50? No, they're not. There's a 0.2 chance that you're going to get it correct and a 0.8 chance that you're going to get it incorrect. So things have to change here for this distribution, and that's the purpose of this lesson. We're looking at a distribution that isn't 50-50, okay? So I'm going to go ahead and tell you that this is not going to be a symmetric normal distribution like you saw with that Galton board that I showed in the video. This should not be symmetric. This should be skewed. It's almost like I'm taking the probability and I'm saying, okay, I'm going to take it, I'm going to tilt it to the left, tilting it this direction, and it's more influenced to go to the left. So we saw what happened with that. We should have more outcomes. It's more likely that it's going to go to the left. So this means that we have to actually change what we got here, because right now there are still 1,024 combinations that work for this if we're creating the probability distribution. Let me go ahead and make a new slide here with this, and we're gonna do some of our work on here. So let's make a new page. So you've already written most of this. I'm gonna paste this in here. We are going to go ahead and make the probability distribution for this. Okay. So we have X is the number of correct guesses, and we're trying to get that to be 7 or more so we can pass, right? So we're gonna go ahead and define our variable X equals number correct. That looks so bad. Okay, number correct. Okay, so how many total combinations are there for these? Well, there's going to be the same as if I flipped a coin 10 times, which is what I just said. So we're going to go ahead and draw your distribution with me here. So this is 0. You could get 0 correct. 1, 2, 3, 4, 5, 6, 7, 8, 9. Is that right? Wait. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's fine. Okay. So I'm going to go ahead and type all this in. I'll pause it. You're going to just fill yours in with me, but I'm going to pause I'm going to go ahead and skip ahead to that part. Okay, so we have these. This is what I've got so far set up. Now, we don't want to do this yet. We do not want to put one combination here. So if you get none right. Now, obviously, there's one combination to where you're getting none of them correct, but it's not the same as what we had with the coin flip, 1 out of 1,024, because it's not even probabilities. You are actually more likely to get none of them correct than you are to get all of them correct. So this is not true here. So don't draw this in there. This is not true that you have an equal chance of getting all 10 correct as you would missing all 10. Missing all 10 is more likely because you have a 0.8 chance of missing the problem. So we have to adjust what we're putting in here. We're not going to be able to go with what we did up here with the coin flips. Okay? Now, I think I had you guys write down, let me pull this up. I think I had you guys write down this rule right here. This is what we're going to need. So I need you to find the probability for each of these. What we did last time was the number of arrangements out of the combinations that were total, but we have to change that up now, okay? So we're gonna need what I circled. Let's go ahead and copy that into our notes. I'm going to grab that. And this is going to help us find the probabilities for each and every one of these. Let me go back over here, paste. Move this down. All right, this is as far as it's going to go here. Okay, so what we're going to do, I'm going to pull up my calculator, make sure it's clear here. Clear history. Okay. We're going to do this first kind of slow, and then we're going to find a way to speed it up using the calculator. But if I want to find the probability of getting, I'll move this over, of getting 0, right? You take the number of arrangements times, you have this probability formula here. That's how we're going to find each and every individual one of these. So how many combinations, how many arrangements get us exactly 0? Well, there's only one, and we multiply that by P. P is the probability of success, and we already did that. That is what we did over here, right? Here's our probability of success, 0.2. So we go back over here, and we know our probability of success is 0.2. And we're going to raise that to the, what is K? K, if you remember from before, is the number of successes that you want. Well, we want 0 successes times, we have 1 minus P, so that's 1 minus 0.2 to the, we want N minus K. So we're going to raise that to the N minus K, N, number of trials, N, so it's 10 minus number of successes, 0. So we hit enter. There's our probability. So we're gonna go ahead and write that inside of our table. So please go ahead and do that right now. And you'll notice that this is actually different than what we had on our first one. So for this one here, because that's 10%, right? Come on, respond. It's not responding. I've added too many pages to this. That's the problem. Hope it doesn't crash. I'm gonna skip ahead to where this is ready. Okay, so this is ready now. So that's the probability that we got on the last page. If we did this, 1 divided by 1024, we get that probability. It's almost impossible to happen. But now that we have this new probability with that 0.8 actually chance of not getting it correct, look at the difference that makes in this probability of that bottom pathway of getting none correct in the binomial random variable. So that's the key difference here, is we expect this to look quite a bit different. So let's go ahead and all we need to do to continue this process is we just need to copy and paste, and we're just going to be changing this number. So this is a 1. Oh, actually, we got to change 2 numbers. This is a 1. How many combinations result in a 1? Well, we actually have that from our last table over here. Boy, this program is having trouble. So now we know that there should be 10 pathways that get you one correct, right? At least you're getting exactly one correct. There should be 10 pathways in these 1024. So we pull up the calculator. We need to make this a 10 here, okay? And we've changed this. We want exactly one success. That's what's up in the power here. Using our formula, we hit enter, and there's our new probability. So the probability of getting one correct is higher than getting none correct, actually. So let's go back over here, and we're gonna put that into our table. Okay. Then we're gonna repeat this process until we get all of these correct. Now I'm gonna speed this up with the calculator and do something a little bit, I would say, more efficient, if you will. And you can follow along with me. This program is wearing me out right now. While this is loading, let's go ahead and in our calculators make a new document. Don't save. Let's do a list and spreadsheet. We'll call this X. This is P of X. We want our, what did I call this? Combos. This is going to be the number of arrangements. And then this one here is going to be, this is going to be, actually, no. We don't, this is all we need. So we're going to go 1 through 10 on here. Okay. And now we want the combinations. Remember that the combinations are, we have the formula, this one here, combinatorics. So we need to use these, the radicals, which we already know what they're gonna be. They're right here. And the combinations are gonna be the same for a set of 10 trials. So, but I'm gonna go ahead and we're gonna redo that here. So hit equals up in this gray box, make a fraction. We want, and I'm working right here in this space, so we need 10 trials, 10 factorial, over number of successes is going to be X successes, right? So it's going to take this column here, and it's going to put those successes in, and then we want 10 minus X factorial. Hit enter, and make sure that you pick the variable reference. So there's all of our combinations that we have, and we're just putting them in here. Now, we want these probabilities. So we're gonna take, we're using this new formula now. So we're using this formula on the right side of the screen here, and we're putting that here. Now the number of arrangements is gonna be in this column. So we want, we're gonna start with combo in here, C-O-M-B-O. Also, if you can't get your calculator to type combo for some reason, just put the letter C or put any letter that works. And then we want to multiply by, we want probability, which is 0.2. Okay. We want to raise that to the K power. Remember, K is X. And then we want to multiply that. So we're going to hit times. We want 1 minus 0.2 to the, we want n minus k, so that's 10 minus x. And we're going to hit enter. And we want to make sure that we use variable references. So here are the probabilities we need. Okay? So this is really nice that we're able to just auto-generate all of these. So I'm going to, you're going to write these down in your notes. I'm going to copy and paste these in. So you can do that with me while I'm working. I'm just going to go to three places here. I'm not going to worry about my rounding right now, just because I want to get this done quickly. And I'm going to go ahead and skip ahead with all of this filled in. Okay, so after all of that, I have filled in this table for the probabilities. Okay, and you can see the one that's most likely to happen is you're going to get 1 or 2 correct. That's what should happen, and that should make sense. Think about it. You're expected to have 20% probability, right? So you're almost expecting 20% correct. So 20% of 10, oh, that's 2, right? 0.2 of 10 is 2, right? Let's, in our calculators, we can actually graph this distribution. Remember, we've seen the other ones where they're symmetric, just like that Galton board. If you hit menu, data, summary plot, let's make this x and p of x, new page, we see a very obvious skew in this data. And you'll notice that you can't even, it doesn't even show, because they're so small, it does not even show up to 10 because it's tiny. It does show this one. This is 0.5% that it's showing there, but the rest of them are just microscopic. So look at this distribution, it's skewed to the right. And this is what happened in the video when I turned that Galton board to the left, just slightly, it influenced all of the balls to go to the left. So we're seeing that work right here on our calculator and in this distribution. So let's answer these questions. What is the probability of getting exactly 7 correct? Well, we've answered that. So this is the probability you pass, 0.005. Did I do that wrong? Hold on. Let's get back over here. 7, because that's the same as, oh, I did do it wrong. I got these mixed up. Okay, hold on. So this is 007 goes here. Hold on. I'll fix these real quick. All right, those should be fixed now. So 0.007, so it's even worse than what we had put initially. So this is 0.07, 3 zeros and a 7. Terrible odds of passing. Like, it's not gonna happen really. It's 0.07%. Just terrible. All right, what about the probability of getting more than 7? So that is 7 or more, right? So that's going to be the cumulative probability of these 3 here, okay? That's what that cumulative probability is. Now, for us to do this, I want to use that binomial CDF. Instead of sitting here and adding them, now adding them will work, but we want, we can actually have the calculator do this for us. Let's do the binomial CDF. So we go on our calculator here, go back to your calculator page, hit this little left side over here, menu 5. Since we're doing a cumulative distribution, we want binomial CDF, 10 trials. 0.2 is the probability of success. What's the lower boundary? It's 7. Upper boundary is 10, right? Okay. So we're going to hit OK. There's our probability right here. So I'm going to copy and paste that in. So it does not improve at all, or hardly improves at all on this. Don't put it in scientific for me. Come on now. Hold on. Well, 3 zeros, and I'll run that to 9. So 3 zeros and a 9. There we go. All right, so now what's the probability that it's less than 7? Okay, what's the probability it's less than 7? So we're going to redo this binomial CDF menu, 5, and we want binomial CDF again, 10 trials, probability of success is 0.2. We want the lower boundary to be, well actually, since it's less than 7, we go from 0 to, what's the upper boundary? Is it 7? No, it's actually 6 because it's not inclusive. We don't want 7. 7 was on the last boundary, so this is 6. We hit OK. There's your probability of failing. And I'll even do 4 decimal places on this one. Probability of failing is 0.9991. And E says, is it likely that a guessing student will pass? It is very unlikely. Very unlikely that you're going to pass. 0.09% chance. Okay, that is not a good chance. It's kind of amazing that a student actually got 7 at one point. I'm interested to go back and look at the play pause it for the grades on this just to see how you guys did and see if we got anybody, because it is a rare thing to do just by guessing. Okay, very rare. Okay, we're going to talk about one more thing in this video, and this is actually going to close up binomial distributions. we want to find and we want to calculate the mean and standard deviation for binomial random variables. So go ahead and put that in your notes. And we are going to we're going to go back over this left screen here, and you need to write these right here. I'm going to highlight those just to make sure we know what we're writing. Okay, so let's go ahead and write down those formulas, and pretty straightforward formulas right there. The big key is these formulas will only work for binomial distributions. So go ahead and write these down. Pretty simple. And I'll write them on my slide here while y'all are getting those written. I'm not pausing the video this time. I'm just trusting that you're going to write these as I'm doing this. And remember, this is called the expected value. This mean, it's what we expect to happen. And we already said we expect to get 2 correct because of the probabilities. So our mean should be 2. Okay, let's go back to our main display here. Well, let's find the mean for this situation here. Well, it's n times p. What's n? Well, that's the number of trials. It's 10. What's p? That's the probability. It's 0.2. What's 10 times 0.2? That's 2. So the mean for the binomial random variable is 2. Let's go back to the calculator again just to double verify this. Going here, that's right here, right? We're expecting that to happen. It skews to the right. Okay, most everything's going to happen here, but the expected outcome is you're going to get 2 correct. Okay, let's do the standard deviation. This is the spread of the data, square root. We want n, which is 10, times p. This is the mean, is what it is, so times 0.2. And then we're going to do times 1 minus 0.2. Okay. I'm going to use my inspire for this. So I want square root 10 times 0.2 times 1 minus 0.2. So this is our value. 1.26 is the standard deviation. So you expect outcomes to be within 1. And you can see that. Look, it's these are still pretty likely to occur here. Everything else beyond that is pretty rare occurrence. You could get 4 correct, you could get 0. So if I go back and look at the scores, this is what our class's distribution of scores should look like. This is what should be happening. Yeah, sure, you'll have some that get up here, and that's fun and impressive, but you should not rely on this method and this technique for a multiple choice test, especially a 25% probability would look way different. I think I could do that really quick, actually. Let's see. Combo. Yeah, if I change this to 0.25, let's see how that affects things. Because that would mean you're supposed to get 25%. Nah, it doesn't change it too much. I mean, it's 2.5, so it doesn't change it drastically. There it is. Yeah, it does shift things a little bit, but not that much. And you can see 7 is now visible, whereas before. Let me go Control Escape. Before you couldn't even see the 7. So you have better odds, obviously, with 4 question multiple choice, but not with this. So let me pull up a couple documents and then I'll end this. So let's look at the dual credit sheet. So for my dual credit students, on this probability sheet, you will see mean right here. You have that available. This isn't a formula you have to memorize. It's right there for you. And then you have your standard deviation. Now you'll notice that it has Q there, which is different from what what our PowerPoint had. Where did that go? It's a little bit different from what we actually wrote in our notes, which was n times p, 1 minus p. But q is this. It actually defines what q is right above that. So you're not going to be like, well, what the heck is q? It tells you what q is. It's 1 minus p. Okay? So that's in your formula sheet. AP students, this is the first page of this. You see it right here, binomial distribution. It gives you these combinatorics and the binomial coefficient. Dual credit students, you don't have to worry about memorizing this, and obviously AP you don't either, but it's there. You have to know how to use it. Here's your formulas for mean and standard deviation. So these things are there for you, and you will have these on the next test if it asks you to find the mean and standard deviation. Let's look at the problem set really quick, and then we'll be done. So AP students, you now have the tools to do these problems here for 32 and 33. You'll notice how these say AP only on here. Dual credit's not going to have to worry about that. But let's look, and then there's a couple more here through these. I'll need to go back and talk about this right here with you guys. Where's the one that I want? Hold on one second. Okay, so here 34 and 35, it says a survey asks a random sample of 1,500 adults in Ohio if they support an increase in the state sales tax from 5% to 6%, with the additional revenue going to education. Let X denote the number in the sample that say they support the increase. Suppose that 40% of all adults in Ohio support the increase. So it says, what is the mean? So what's going to happen, this is binomial because you're going to go up and ask somebody, do you support it or do you not? And you're counting the number that say I do support it or I don't. So it's binary. Each person you go to should be independent, right? That should make sense. Here it's giving us the probability that somebody is going to support it, 40%. So that is our probability, P. And then the probability shouldn't change from person to person because that idea of independence. So which of the following is the mean of this binomial random variable? Well, we're going to use our formula. Let me go ahead and write on this. We're using n times p. So what is n? N is the number of trials. We're going to go ask 1,500 people, right? That's the sample size, 1,500. What's the probability they're going to support it? Well, they tell us that right here. So times 0.4. This should give us our answer, and that's how straightforward it is to calculate these binomial means. So we expect 600. That would be the mean of that distribution. Next, which of the following is the approximate standard deviation? Well, n times p times square root of n times p times 1 minus p. Again, pretty straightforward formula. We already know that this is 600, right? We already got that. So it's 600 times 1 minus 0.4, which is the probability. Pull up the inspire. Let's do our square root. Oops. Square root 600 times 1 minus 0.4. So 18.97. You'll notice they round that up right here. So it's 19, and that should make sense. There's the mean is 600. You should be able to deviate by a larger number. Okay. All right. So that's going to be it, folks. These videos have been pretty long, but we are done with binomial random variables. I thought I was going to have one more video, but we don't really need that. We are going to end up doing some practice. I'll probably make one more video talking about practicing with that, and we're going to be using Delta Math to work some of these problems. So expect some more videos on how to get signed up for that, and then how to work some of the problems. But we're going to stop this one here.